Today we will be looking at the various aspects of enzyme kinetics. So, just to give you a recap, we have seen that the way in which the enzyme functions is by, if you consider this as the uncatalyzed reaction, the delta G double dagger, it is possible that it stabilizes the transition state and goes through perhaps a series of small intermediates and transition states, where the net effect is that it lowers the barrier. And the barrier, as we know, is a function of how fast a reaction proceeds. Now, so this delta G double dagger, that is now the new delta G double dagger, is going to be significantly lower than the uncatalyzed reaction. Alternately, we also have found, or we have also seen, that the ground state energy of the substrate can go up due to binding, and so this also results in some sort of a lowering of the barrier. So, if you imagine that both of these processes are happening, then you can think about synergy that occurs and a substantial increase in the rate of the reaction. Now, let us look at some aspects of enzyme kinetics. So, in order to first understand how enzyme kinetics, how this process happens, let us propose a reaction of substrate going to a product. We can propose an intermediate where the enzyme binds to the substrate and forms a substrate enzyme complex, which is referred to as ES. And then the enzyme substrate complex degrades to give you back the enzyme and the product. So, we will look at the mathematics of this later, but you can think that at low concentrations of the substrate, the rate of the reaction almost increases proportionally to the substrate concentration, whereas at high substrate concentration it goes up and then it plateaus. So, the x axis and y axis of this plot are rate of the reaction is in the y axis and the substrate concentration is in the x axis. So, at high substrate concentrations, the rate almost becomes constant and approaches a maximum. One can understand this by thinking about the relationship between the substrate concentration and the enzyme. When more substrate is present than active sites available, therefore, increasing the amount of the substrate will have no effect. So, one of the ways in which we understand enzyme kinetics is to do what is known as a Michaelis-Menten treatment. So, we define a term Km, which is half of the maximum rate. Okay. It is called the Michaelis constant. Km is the concentration of the substrate at which half the active sites in the enzyme are filled. Okay. So, in this plot of rate of reaction versus substrate concentration, which we have just looked at, the Km is defined as the point where half of the rate maximum is obtained. Okay. So, the way we obtain this is to draw a line from here to here and then go down, and this is the concentration at which you get Km. Right. This in turn provides a measure of the substrate concentration required for significant catalysis to occur. Let us now look at how we can interpret Km. Km is also related to the rate. So, Km is basically K2 plus K3 divided by K1. So, consider now the situation where there is rapid equilibrium between the substrate and enzyme substrate. So, that means that this process is extremely fast. Okay. So, the substrate binds to the active site and then departs, binds to the active site, departs, does this again and again and again, and then in one of these situations it then goes and forms the product. So, therefore, the formation of the product is significantly slower than the rapid equilibrium that happens between the enzyme and the substrate. So, the dissociation rate K2 of the enzyme substrate is much greater than the rate of formation of the product, which is K3. So, you can approximate this equation to K2 divided by K1. So, how do we get this? So, K2 is much greater than K3. So, in that case you can remove this term because it does not add much value to the numerator, and you end up getting K2 divided by K1. So, in this situation the Michaelis-Menten constant Km effectively equals the dissociation constant of the enzyme substrate complex, and it can be taken as a measure of how strongly the substrate binds to the enzyme. So, for the equation that we are looking at here, Es going to give you, this is the equilibrium that we are looking at, right. The dissociation constant is nothing but the concentration of the enzyme multiplied by the concentration of the substrate divided by the concentration of the enzyme substrate complex. So, a high value of Km indicates weak binding because the equilibrium is pushed towards the right, whereas a low value of Km indicates strong binding because the equilibrium is towards the left. So, therefore, the Km is a very good measure of how well the substrate binds to the enzyme. Okay. So, the maximum rate is related to the total concentration of the enzyme, which is basically nothing but the total concentration of the enzyme plus the enzyme substrate complex. So, the rate max that we can attain is basically K3 times the concentration of the enzyme in total. So, knowledge of the maximum rate and the enzyme concentration allows us to determine K3. So, K3 is the rate max divided by enzyme total. So, what we would get here is, if you look at the rate max for the turnover of a particular enzyme, you get a value of 0.6 molar per second, which is in the numerator, and the concentration of the enzyme that we have started with is 10 ⁻⁻⁶ molar, which is 1 micromolar. So, if I divide these two numbers, then I get a value of 600,000 per second. Okay. So, this is quite a large number for of turnover. So, the example that looking at here is carbonic anhydrase, which basically converts carbon dioxide to hydrogen carbonate. A very important and convenient way of looking at enzyme kinetics is to use the Lineweaver-Burk plot. Okay. So, this plot actually provides a more accurate value of the Michaelis constant Km. The maximum rate can then be obtained from the intercept of this line. So, now let us look at what this equation is. So, we take 1 by rate equals this term over here, right. So, now if we plot 1 by rate versus 1 by substrate concentration, this is called the Lineweaver-Burk plot. So, you can think about this equation here that I have shown up as y equals mx plus c, and you will end up with a term with a straight line. Okay. And there are a number of important parts of this straight line that we need to understand. I am not going to go through the derivation of this now, but this is something that you could do on in your own free time. Okay. So, here we will look at certain parts of this plot and try to figure out what is going on. So, the intercept over here is minus 1 by Km, and the point here where the the line meets the y axis is minus 1 by rate max, and the slope is nothing but the Michaelis constant Km divided by rate max. So, a number of important parameters about the enzyme can be obtained by this Lineweaver-Burk plot. So, studies of enzyme kinetics are extremely useful in determining the properties of an enzyme inhibitor. So, let us say you want to set up a large scale screen for determining or for identifying a new inhibitor for an enzyme. We need to first be able to understand the kinetics of the enzyme, and then and only then we will be able to find out the inhibitor and which inhibitor is more efficient or which inhibitor is less efficient. So, Lineweaver-Burk plots are used to determine what type of inhibition is occurring, as well as other important quantitative measurements that are related to that inhibition. Okay. So, in the case of a competitive inhibition, which we have looked at previously, the line crosses the y axis at the same point, that is, the maximum rate of the enzyme is unaffected, but the slopes are different. So, if you were to look at how a competitive inhibitor functions, you will find that this point here is going to remain the same, whereas the slope has changed. Okay. So, the fact that the maximum rate remains unaffected reflects the fact that the inhibitor and the substrate are competing for the same active site. So, remember when we are looking at an enzyme and a competitive inhibitor. So, here let us say this is the natural substrate of the molecule and this is our inhibitor. They both go and bind to the same site. So, when you have an inhibitor, it is going to go and compete for the same site for binding. So, therefore, increasing the substrate concentration. So, if I have more of this substrate, right, what it does is that it will overcome the inhibition and therefore, the rate max does not change. Now, the increase in the slope that results from adding an inhibitor is a measure of how strongly the inhibitor binds to the enzyme, okay, and decreases the rate of the enzyme catalyzed reaction. So, we have already looked at that this value is nothing but minus 1 by Km, right, and the interpretation that we made about Km is how tightly the enzyme binds to the substrate. And so, in the presence of a competitive inhibitor, the value of Km is going to change, and this means that the inhibitor is going to bind strongly or weakly. We can find that out by this plot. Now, let us define a term alpha, which is the degree of inhibition. Okay. So, in the presence of the inhibitor, you have a Km, which is Km apparent, which is nothing but alpha times Km. Okay. Now, a useful measure of the inhibition is the apparent inhibition constant Ki. So, Ki, which is an equilibrium constant, is a measure of how well the enzyme inhibitor dissociates and becomes associated again, right. So, this Ki is defined as the concentration of the enzyme multiplied by the concentration of the inhibitor divided by the concentration of the enzyme inhibitor complex. So, we can write an expression Ki is equal to concentration of I, which is the inhibitor, divided by alpha minus 1, and alpha, as we recall, is the degree of inhibition. Now, replacing alpha with Km apparent by Km and then rearranging the equation gives us a straight line equation. The straight line equation is nothing but Km apparent equals this term Km by Ki times concentration of I plus Km, right. So, if we were to plot Km apparent versus the concentration of the inhibitor, then we could get some important values from this plot. So, what we would expect is we would get, if the y axis here is Km and the inhibitor concentration is the x axis. Now, we would expect to see a straight line with a slope, and the slope is nothing but Km divided by Ki, okay, and the y axis intercept should be Km. When the inhibitor concentration is 0, we would expect no inhibition, and that should give us the Michaelis-Menten constant of the enzyme with the natural substrate. To create this plot, what we need would be a series of Lineweaver-Burk plots, and then we would get the values of Km apparent at different inhibitor concentrations. Then the plot of Km apparent versus I gives us Ki to be calculated from the slope of the line. Now, Ki is a measure of how good the inhibitor is. The lower the value of Ki, the more potent the inhibitor. We have already looked at the other cases of inhibition other than competitive inhibition, which is uncompetitive inhibition. Okay. Uncompetitive inhibition happens when the inhibitor binds to the enzyme substrate complex rather than the free enzyme. So, enzyme inhibition studies which result in Lineweaver-Burk plots where the lines are parallel and cross the y axis at different points. So, you have this is parallel to the first line that we have drawn in the absence of the inhibitor, then you could infer that it is an uncompetitive inhibition. What actually happens here is that because the inhibitor is going to bind to the enzyme substrate complex, the maximum rate is going to reduce. Now, let us look at the last case, which is a non-competitive inhibition. So, for a reversible non-competitive inhibitor, the lines have the same intercept on the x axis, that is the Michaelis-Menten constant remains unaffected, but they have a different slope and different intercept. Okay. The intercept is different because the rate is going to change, the enzyme is going to be inhibited in a non-competitive manner. So, therefore, this Lineweaver-Burk plot, if it shows a situation like this, where you have the same Km, but you have slopes of which are different, then one could infer that non-competitive inhibition is actually happening. Now, let us look at another term which is very useful, which is IC50 or inhibitory concentration 50%. So, when we want to compare across various enzyme inhibitors, the value of IC50 is very often quoted. This is nothing but the concentration of the inhibitor required to reduce the activity of the enzyme by 50%. So, compounds with a high IC50 are less powerful inhibitors, and those with a low IC50 are better inhibitors.